All right, this is section 12.6, cylindrical and quadric surfaces. This one is definitely going to take a couple of videos at least. And outside of our last chapter that we cover in Calc 3, this is probably the one that's going to entitle the most visual and spatial awareness. I'm going to definitely do my best to sketch these things so that you can kind of see what they look like, but this is all about three-dimensional surfaces, so we're going to have to do our best to visually see. And the reason I want to make sure that we sketch these is because you get a much better feeling for what's going on if you're able to sketch these things as opposed to just putting up a picture of something that you find. We'll do that for all except for one of them. One of them is just way too hard. Okay, so we're going to try and sketch and identify the graphs of quadric surfaces. So the first thing we're going to talk about are cylinders. And the way you guys probably have been taught or have thought about cylinders is not exactly what you would think. So first of all, the equation of a cylinder is going to have one variable missing. What do I mean by that? Let's write that down first. One variable missing. That variable, specifically whatever it is going to vary. So if you look at the equation below, y equals x squared, that's an equation that we are certainly used to in 2 dimensions. That's your basic parabola. But in 3 dimensions, it's missing a variable. It's missing the z variable. Well, that z variable in this case is going to vary. So the basic thing to do is to think of it, first of all, in terms of 2 dimensions. So in 2D, we know that this is just a parabola. In 3 dimensions, however, and we have to draw this 3-dimensionally, let's see how well we can do here. So this is our z, x, and our y. If you were to sketch a parabola in the xy plane, your basic parabola in the xy plane would look something like this. Let's see how well I can do this. On the positive side, it'll look like that. And then on the negative side, it would look like that. I don't like the negative side so much. Let's try that again. That's a little bit better. Trying to make it a little more symmetric. So it's going to look something like that and keep on going forever. Now, obviously, since it does go on forever, we cannot possibly draw the entire thing. But we're going to draw just basically a portion of it so that we get the idea. Obviously, this does go on forever in the positive y direction, as well in the positive and negative x direction. But we're only going to draw a piece of it. So basically what we need to do is we need to show that this is going to vary in the z direction. So because it's going to vary in the z direction, it's going to be parallel to the z-axis. So from the endpoints here, I'm going to draw something which pretty much goes up. I'm going to try to approximate those at the same length, and I'm going to try to do the same thing on the z-axis here, trying to approximate that at the same length. And then we're going to try and connect all of those pieces in somewhat of a parabolic form. So it's going to start here, around here, and then connect there. Something like that. So as you can see, mine is not the best drawing there, but it kind of looks like I don't know, like a sideways skate ramp or something like that or whatever. But that, believe it or not, is a cylinder. Now, it's not a full cylinder. It's not the kind of cylinder that you're used to seeing where where it encloses itself. This one is based upon the base as a parabola, so we call it a parabolic cylinder. Parabolic cylinder. So a cylinder does not have to enclose itself. It certainly can, but in this case it does not. So again, I'm hoping that you can see that. Let me see if I can make this a little bit better. Let's connect that right on the outside there so you can kind of see it. That makes it a little bit better. If you were really good at shading, you could probably do this even better than I can. But that is a parabolic cylinder. So what you're looking for is something with only two variables. One variable is missing. That variable will vary. So obviously this thing would go up infinitely in the z direction. Again, I cut it off at, maybe z equals 2 or something like that. I don't know exactly. And it goes down forever in the z direction as well. And then it obviously, because it's a parabola, it extends in the positive y direction as well as the positive and negative x direction infinitely. We can only draw a small portion of it. Okay, so let's go ahead and look at the next one. Example number 2. So once again, you should be able to see you've got z equals 4 minus y squared, and this one is missing the x. So that means the x part is going to vary. So let's go ahead and sketch our x, y, z axis. There's z, x, y. Make that an actual y. There we go. All right, so according to this, the x is missing, so it's going to vary in the x direction. So if we were just to kind of real quickly sketch something in two-dimensional space over here, this would be the z-axis, this would be the y-axis. That parabola looks like it opens down in the y direction, and it's got a z-intercept of 4, so it's going to look something like this. In two-dimensional space. So we have to kind of sketch that general idea in two-dimensional space. Also, these points right here are going to be the y-intercepts, which looks like that would be plus and minus 2, because if you set z equal to 0, then you would get positive or negative 2. So let's go ahead and I'm going to do my best to make this actually look accurate. 1, 2, 3, 4, 1, 2 in either direction on the y. Something like that. So now we can sketch, or at least try to, our parabola. I missed. That was almost really good. There we go. All right, so that's what it looks like on the YZ plane. Again, obviously it goes on forever. It goes past the y-axis in the negative z direction forever. We're only drawing a portion of it. So now I'm going to do my best to extend this parallel to the x-axis, because remember it varies in the x direction. And then we're going to go ahead and as you can tell, I tried to keep the line in between the end of the red things parallel as much as I could to the y-axis so that I can get a symmetric looking shape here. And then I'm going to try to draw that the best that I can. Close, not really good enough. I'm going to try again. Definitely want to use your pencils on this stuff. That looks much better. And then obviously what you could do if you wanted to is just you could kind of, let's do this in blue I guess again, is you could kind of connect the top here to kind of show that it's got some kind of depth or dimension or whatever. Probably would have been better now that I'm looking at it to connect it maybe from here. I don't know, let's see. Yeah, that looks pretty good. It's not the best again, but you get the general idea. So it kind of looks like a tunnel. But again, it is a parabolic cylinder. So it's exactly the same as what we did above. This is going to be a parabolic cylinder. And that's because the trace of it in two dimensions is a parabola, and it's a cylinder. All right, let's move on. So let's take a look at the graph of x squared over 4 plus y squared equals 1. Again, we're going to do it in three-dimensional space, but let's go ahead and take a look at what this looks like in two-dimensional space. Again, we're missing one variable. We're missing z, so it's going to extend in the z direction infinitely both directions. So let's go ahead and trace it in the xy plane. So if you haven't already recognized, and this is kind of why we do the last summer assignment that I gave to you guys, this is the equation of an ellipse. So if you were to plug 0 in for x, so basically we're trying to find the y-intercepts, it looks like the y-intercepts here are going to be positive and negative 1, positive and -1. If I were to plug 0 in for y, we're going to get the x-intercepts, so multiplying both sides by 4 would give me x squared equals 4. So it looks like my x-intercepts are going to be positive and -2. So now we can go ahead and just kind of sketch our ellipse here, best that I can. Whoops. That's not too bad. Kind of missed my 2 in the bottom, but it's close enough. I'm not going to worry about that one. So there's our two-dimensional ellipse. So if you haven't already guessed it, we're going to call this one an elliptic cylinder because that's exactly what it's going to be. So here's our x, here's our y, here's our z. Kind of extend the x and the y in both directions. So let's see. Let's go ahead and put some marks on here. The x was out 2 in both directions, so 1, 2, 1, 2, and it's only 1 in the y direction, so I'll need 1 there and there. So let's go ahead and sketch the cylinder through those points. And then again, it's going to extend infinitely in both directions. We can actually show this one a little bit better than we had before. So this one's going to extend infinitely parallel this direction and parallel this direction. Again, trying to keep that parallel to the x-axis the best that I can. Something like that looks okay. And then we will try to draw the elliptical shape on the top and the bottom. And hopefully what you can see there is you've got a cylinder. This one is completely enclosed because the base of it is an ellipse. So this is more like the kind of cylinders you're used to, but the base is an elliptical shape. So this is an elliptic cylinder. Okay, honestly, cylinders are probably one of the easier ones for us to recognize and be able to sketch because the traces are usually things which are relatively common, things that we're used to. Of course, I say that, and then we're going to do the next. Whoops, we're going to do the next one. So if you recognize this one, it looks very similar. In this case, the y is missing, so the y part is going to be the part that varies. But you notice that there's a minus sign in there instead of a plus. So this one's going to be a hyperbola. In 2 dimensions, this is a hyperbola. And so this is going to be the x, this is going to be the z. If you were to plug 0 in for z, you're going to get x is plus or minus 2 for our intercepts. And if you were to plug 0 in for x, you're going to get negative z squared equals 1, which means that z squared equals -1. Well, that can't happen. It's imaginary. It's going to be in the imaginary plane. We're not dealing with that. So that's why there are no z-intercepts here. So if you remember correctly, the hyperbolic shape looks kind of like 2 sideways parabolas. They aren't really parabolas. They just kind of resemble that. And then there's asymptotes that go in between, all that kind of stuff. For this purposes of our sketch, we don't need to worry about that. Now let's go ahead and translate this to a 3-dimensional sketch. Again, let's extend these axes just a little bit. Okay, so our z, x, y. All right, so now the hard part here is going to be visualizing how this is going to look spatially. So I do know that in the x direction at 2 and -2 are my intercepts. Okay, I have to kind of somehow draw a hyperbola. So let's see if we can do this. So it looks like the hyperbola going through here is going to do something like this. Okay, that's not too bad. And then on the other side, it's going to do something like this. Okay, not horrible. I'm going to probably have to do a little bit of erasing here and dot some of this stuff because I think some of this is going to be in the background, but we'll work with it. All right, so now I know I have to stay parallel to the y-axis. That's the top. This is the bottom. This is the top. This is the bottom. Now I'm going to do my best here to sketch the other part of this. So this one is going to do this, come around here and hit the bottom. This one is going to do the same idea, come around and hit the bottom. And then probably the best thing to do is going to be to cap these things off. So it looks like I'll have a cap here. Let's see if I can draw that. Not the best. And then I've got a cap at the bottom on this one. You can kind of see it. Like I said, it kind of looks like two sideways ramps or something like that. Again, I probably should have, I don't know if I can do this or not. Let's see if I can. Oops, get the eraser. Maybe kind of dash that piece right there so you can kind of see it's behind. And then I guess technically the piece right in there would be dashed. Not the best. But anyway, hopefully, again, you can see how these things open up. And again, they go infinitely in the y direction, so I could have gone into the negative y direction as well. Could have gone more into the positive y direction as well. And obviously the the hyperbolic shapes go on infinitely in the x direction and the z direction, up and down. So again, this one here is called a hyperbolic cylinder. All right, not too bad overall. We're going to stop this one there after cylinders. I'm going to come back. This will probably be a 3-video lesson. I'm going to try and keep them a little bit shorter. But all right, so there's our cylinders.